Hello, there he is. There they are. There. Hello, Abdel. Top of the afternoon, my friend. Hello, Gianna. Awesome, awesome. Good afternoon. And good. Hi, hi. Hello, more people coming. Hello, more people coming. More people coming. Hello, Miriam. Hello, good afternoon, Stephen. Oh, and there's all smile. Oh, there's like people. It's almost like there's an exam coming. And there's Jose. All right, all right. Hi, Kirsten. Did I say Stephen? Good afternoon, Stephen. Hi, Sarah. Good afternoon, Brianna. Hello, Brian. She made it. Yes, she made it. All smile. Good afternoon, Tobias. Wait, where's the? Oh, now I can see those cards much better. That's awesome. You got to see. Good afternoon, Montserrat. Hello, Ashley. Good afternoon, Jasmine. And wait, who else did I not see? I said Ashley. Jada, hello. Hello, Brian. Is that already? Oh, he's making. I don't know if he's. That's awesome. Oh, hello in 3D. Yes, yes. And speaking of 3D, you know, if you come to my, hopefully at some point people are going to see me in my office someday in 3D or whatever, and maybe only to my, well, anyway, whatever. There's a lot of Pokemon on the door of my office these days. The Pokemon amount on the door is growing. Like, I don't know why. Well, that day, Tuesday, my physical office hours are Tuesdays, top of the afternoon professors. Oh, professor. Oh, I'm sorry. Okay. My Tuesday. So I guess it'll be a little late for this exam, unfortunately, but Tuesday, 11 to 1 is one main time, but I also do Zoom and stuff like that. But physically, I'm in my office from 11 to 1 on Tuesdays. And that's right on the 4th floor there. But if anybody, you can email me and stuff like, oh, that's a bummer. Oh, that's a bummer. Oh, okay. I mean, oh, that's a bummer. Well, we could figure something else, but I can also Zoom and stuff like that. All right, I want to get rolling because I know we've got this exam and everything. I don't know why my board is having problem connecting. 1 second, sorry. Yes, why? Okay, I'm trying to connect the board, but all right, what we're going to do in a second, again, put any questions in the, that's it. Okay. Right. That is a bummer. Oh, you have a bummer, right? Here's what we're gonna do. So I want to go over one more problem in the practice midterm, like in a moment. Let me make it clear again. Okay, I think everybody's clear at this point. Like the exam is going to be posted tomorrow night by 8 o'clock. You're going to turn it in Monday by 3:05 p.m. Again, the two things they're going to be rigid about is you are going to turn it in on time and you are going to show up at class 3:05 Monday. I mean, unless you communicate in advance about any issue that you're having with either one of those things. If you communicate and I communicate back with you, that's one thing. Other than that, definitely turn in the exam for real before 3:05 next Wednesday, and definitely come to class. Hopefully it's clear now that of the practice exam, which is the main point, the main study guide to the actual exam, of the practice exam. Let me repeat again, there's been 2 YouTube videos posted so far, like from Monday, from the 2 different sections of class, and in the 2 YouTubes, I did 2 different problems. So please note that, like in your Google Classroom, they're all there on YouTube anyway, but they're both linked in your Google Classroom. So please note that what I did in the other class was a different problem. I highly recommend that you check that out. Pretty much all the problems, even that we didn't get to, were solved in a packet that I put in Google Classroom. So you should have guides to the solutions to pretty much all the problems. Let me warn you again, though, those are guides. Those are to help you to check your answers, to see what to do, to give you hints. But you don't just copy those and turn that in for your exam. I mean, I think I've talked enough about this to make it clear, but those are all. And so you use those all to help you, just like you use Khan Academy or whatever, or MSRC or anything, or any past YouTube videos Also, you can find YouTube videos of mine from all the past semesters where I go over problems like this, whatever, and you talk to each other. But then when you finally sit down to write your exam, you write things that you understand. You make it as honest, as authentic, as personal, as clear, as comprehensive as possible. Just please, this is my one last plea. Please remember, you're not trying to just give me correct physics. I've already given you the correct physics, and you know that, and I know that. You're trying to prove to me that you really understand the correct physics. And so put most of your effort into making as presentable, as clear, and as comprehensive a document as you can. Think of it almost more like a project than like just a quiz or something, especially because you can take as much time as you need to do that. You know, the easier it is for me to follow your work, the better. So that said, so solutions pretty much exist for pretty much everything, I think, at this point. One of the big problems in the practice midterm that is not solved very thoroughly in the solution packet is the problem called I just forgot what it was called. Sorry. Oh, and there's something in the chat. I'll check in a sec. Sorry. Hold on. I'm getting myself. One of the problems that's very important and very sort of thick and long. Oh, is called free float. The free float problem is not solved. Only bits of it are solved in the packet, but that's the one that I just went over in the morning section. So please hear this. The free float problem, the boat on the river with the riverbank, it's page 6. I spent all of this morning's class going over that, like walking through the solution of that. So that YouTube will be posted and put in your Google Classroom. And all of the notes from that will be in the PDF. You know, the full PDF of today will include the notes from both classes. So just please be aware, we're going to go over a different problem now, because I really do think that's the most efficient. I mean, I think, unless you want to put in the chat, unless you vote against it, but I think the best thing for me to do is, go over, well, I'll tell you right now, what I'm planning on going over right now. Well, let me just look at something's in the chat. What? Sorry. Yes. Oh, great. Sarah's question in the chat is perfect. Yes, perfect. That's perfect. If she has a couple of, and it's not just her. If anybody has like quick-ish things, today's definitely the day. And please, and yes, and yeah, I'll pause for a second to get those questions. You can either put them in the chat, or I'll pause for a second for you to ask in voice. But yeah, okay, here we go. Okay, so yes, but before I even look at that, okay, no, I will look for the practice midterm on question 2, the chapter. Oh, that's a great question. Okay, seriously, let me be careful. I'm going to go. Sarah's question is great. Like, I have to say, so I hope you can see in the chat, she's asking, and I'm using, anyway, for the practice midterm on question 2, the chopper, I do not understand why the package has 0 distance. Like, I understand half of the problem, but I get confused on the 0 meter part. That is such a great question, because that really shows, okay, that is someone, I don't want to embarrass anybody, but you only someone who's actually preparing and working through this could possibly have asked that question, number 1. Number 2, and I'm going to answer it, but number 2, honestly, like, for her to be worried about that issue, that's exactly the issue of the problem. That is the thing that you're supposed to notice. Like, there's an answer. Like, it's not a mistake. I'm gonna explain what she's asking. But like, I just want to encourage all of you, I mean, not to get too crazy, but like, this is the thing of physics. If you are worried about a thing like that, you are worried about the right thing. It means you are thinking like a physicist, and you're paying attention, and you're going to get something out of this whole class when we're done, because that's precisely the purpose of the problem, is to raise that concern. So let me answer that. I'm going to answer that in a minute. Let me just, let me get my board back working again, because but yes, and I may even want to screen share what she's talking about. Hang on. I'm just trying to fix the board, but yeah, great. So, and you might want to look at what I will address that before I go to what I was going to. And if other people have other questions, also, I think once I get my board working, I think I can answer that somewhat concisely. So it is sort of a perfect use of our time. So if other people have other questions like that, please also put them in the chat. But for the moment, live trans. Oh, good idea. Good idea. Hold on. Okay. Okay, so now there's live transcription as well. Cool. I love when you guys say that. Also is great. Whoever just, I don't know who asked for that, but you should be praised, whoever just asked, because that seems cool. All right, I'm going to screen share what Sarah is talking about, and I'll try to be somewhat quick about it. And then I'll tell you I'll tell you what I'm planning on talking about today is the Wile E. Coyote problem. Oh, I just lost it. Because I think that's the remaining big problem of the whole thing that didn't get, but okay, she's talking about, here we go. But this is great. It's better for me to answer. Okay, I gotta shut up. I get too excited about these exams. All right, can you see? Yeah, you can see, I think. Okay, so she's talking about this problem here that's one of like the warm-up ones. And I'll even say these warm-up ones, these are perfect examples where these will be on your exam, but these solutions were done out explicitly enough here that for sure I would change numbers on your exam. Or I'll tell you right now, if you're paying attention, on problem 1, the purple plushie, the most obvious thing that I can change there that I probably would, that you might want to practice or try on your own first, is I would probably change it so that the purple plushie was thrown up rather than down, and then change the numbers accordingly and have you figure out the upward speed. It won't change any of the methods at all, but you have to think about it. Anyway, just that's a hint. That's probably what I would change on that one. But now, okay, on Sarah's chopper problem. Okay, I'm gonna, so yes, okay, so we've got this chop. I'm going to assume you're reading it. I'm assuming you're somewhat familiar with it. You got this chopper going, and I'm assuming, again, you've got a solution for it. So I'm going to talk in broad terms here to answer. I'm not going to walk through the whole solution. I'm going to assume you've got a solution in front of you, but I'm going to address the thing that is challenging about that solution. Like, we've got this chopper that's going up, it's accelerating up, and at some moment that we call t equals 0, like the rope is cut, so this package starts free falling down. So, we've got the rope is cut, and a package begins to free fall while the chopper continues to accelerate up at that rate of 5. And you're asked, how far apart will the chopper and the package be like 4 seconds later? Okay, so first of all, one thing I'm sure is clear to Sarah, but let me say to everybody, the method that I'm doing here is I'm doing a separate calculation for each object. I'm using y equals 1/2 at squared plus v naught t, applying it to the chopper to find out how far the chopper goes, how far the chopper gets displaced during the 4 seconds. Then I'm applying it to the package separately, finding out how far the package gets displaced in the 4 seconds. And then I'm going to basically subtract the two answers. Or I'm going to say if this one went this far and the other one went this far, then the displacement between the two is one minus the other. Okay, and so far, that's the part that Sarah understands, I'm pretty sure. Also, what I think she understands, and what hopefully many of you understand, is when I do the equation for each of the two objects, the reason I'm going to get different numbers for each of the two objects is one of the objects, the chopper, is accelerating up at 5 meters per second squared, whereas the package is in free fall, so it's accelerating down at 9.8, or what you could call 10 meters per second squared now, right? Both of them have it. Well, okay, that's the difference, is that they're both accelerating at different amounts in different directions. Now, here's where something interesting comes into play. I mean, first of all, if I were doing out a solution as I did there, I'm going to call the upward direction positive. I'm going to call the downward direction negative. Okay, the package is in free fall. Free fall meaning that its acceleration is pointing down at a rate of 10 meters per second squared, constant. It's accelerating down at a constant rate no matter what. Like, there's no influence on it whatsoever besides gravity. That's the package, is free falling. Here's the hook. Here's the hook is, remember, free fall means just that, what I just said, that the acceleration points down and is a constant amount of approximately 10 meters per second squared. But that's what free fall means. But free fall does not have to mean velocitizing down. In other words, we had some practice problems prior to this where we made it clear that if I throw something up in the air, from the minute it leaves my hand, even while it's traveling up, even while it's velocitizing up, we still consider that free fall, even though it hasn't started to come back down yet, even though it's moving up, it's still called free fall, because even while something is moving up, it still has an acceleration pointing down, meaning in physical terms, if I throw something up at, say, 50 meters per second, it goes up at positive 50, then a second later, it'll be going up at a positive 40, then positive 30. These are velocity numbers I'm giving. In other words, it'll be losing velocity. The velocities will be getting less and less and less. So it'll be like positive 50, positive 40, positive 30, positive 20, positive 10, 0. And then the velocities will continue to get less and less. So they'll go negative 10, negative 20, negative 30, and the thing will start coming down. In other words, free fall does not have to mean that you're moving down. You could be moving up even while you're in free fall. Now, what does that have to do with Sarah's question? That still doesn't help Sarah. What does that have to do with the package? Here's what it has to do with. If you do the calculation on that package, if you do y equals 1/2 at squared plus v naught t on that package, and you plug in negative 10 or negative 9.8, but let's round, which you're allowed to do on the exam. If you plug in negative 10 for the acceleration, you also have to plug in positive 20 for the initial velocity of that package. Like, let's get this straight now. Now, this is tricky. When the package, when the rope was cut and the experiment began, remember, at that moment, the package happened to be already moving up at 20. It was attached to a rope which was attached to a helicopter, which was going up at 20. When the rope was cut, the package was not stationary at that moment. It was already going up at 20, right? So that means it's equivalent. It's literally equivalent. If you were standing on Earth watching this package, you're looking at a package that's just been, it's equivalent to a package that just got thrown up from my hand at 20 meters per second of initial positive velocity. Now it's immediately, now that's also true of the chopper, by the way. The chopper is going up at 20, but the chopper keeps accelerating up because it's a chopper. It keeps accelerating up at 5 meters per second squared. So it's going faster and faster as it's going up. It's always going up. But this package, here comes the like response to Sarah's question. If you look at the math, you're going to see it's 1/2 negative 10 times 4, 4 squared plus 20 times 4, right? If you look at the math, you'll get negative 80 plus positive 80, I believe, which equals 0 for the displacement of the package. In other words, if you just do the math, and this is what I know Sarah still understands what I'm like, this is the part now that she's bumping on, I think. Like, the math says that the package goes a full displacement, a total displacement of zero in the 4 seconds since the rope got cut. And that seems bizarre. Like, meanwhile, the helicopter's gone up like 200 or I don't know, some like number of meters. But that's what the math says, that the package goes nowhere. That 4 seconds later, the package is exactly where it was when it started. And that seems really bizarre because physically what you might well be picturing is some package that you think is like falling down. So like, didn't it go into the negatives? Didn't it go somewhere? And what I'm saying is, what the math is showing us is, if you think about it, I mean, the math is taking very seriously that 20 meters per second of initial positive velocity. What the physics is saying is, hey, when this rope was cut, the package was on its way up. So the package is just like some ball that just got thrown up at 20 meters per second. So it's going up at 20. It's losing 10 every second, but that means it's going to go like this, positive 20, positive 10, then 0. In other words, it's going to go up for a full 2 seconds before it even starts coming down. And then it's going to start coming down for 2 more seconds. So if you watch the package, what it's really going to do, that package it's free falling up, which is a term that we had used a couple of weeks ago to sort of highlight this. The package literally in 4 seconds goes like this, and it ends up exactly where it started. If I had said 6 seconds or something, yeah, then it would land below where it started. But if I had just asked for like 2 seconds, the package would be above where it even started. The package goes up for 2 seconds before it even comes down for 2 seconds. But it's 2 and 2. It happens to be a perfect even. So literally the package ends up being in the same height that it started 4 seconds later. And so the difference between the package and the helicopter is just literally however high the helicopter went. Okay, I'm going to pause for, wait, let me look in the chat. So, but that's a great question. Like, again, note it. I'm going to look in the chat in a second to see if she's okay or if that, but I'm excited that of all the questions for someone to ask, and even though I always take longer than I should, we still have like a full almost hour to do the other problems. So I think that was like a perfect use of time that she asked that. And if there are other questions like that, we still do have time for them. But what I love about that question, everybody, it's another example where a student where we're thinking about physics. She's like, I can see the math, like I see your numbers, but I don't get how this makes sense. And that's what we should all be doing, is like trying to actually make sense out of these numbers for sure, and be a physics class rather than just a raw math class. So okay. So hopefully let me just look in the chat and see what's going on. Oh, sorry. Wait. Oh, okay. Okay. Oh, no, okay, great. No, I appreciate what Sarah's saying. No, okay. Yeah. And and direct chat person, 78.4 is your final distance. Wait, okay, well, first of all, great, Sarah, that's awesome. And well, okay, I'll get to the direct chat person in a second, but also to everybody now, this is the other reason this is perfect. Like, and I really do recommend, I don't always say this, but for this exam, please do watch the YouTube from mostly this class and the morning class, we do the same things mostly, but a lot, I would watch the other, the morning classes for these last 2 days. In one big point I'm trying to make to them, I'm trying to make to you too, is like Galileo's principle of relativity, why I make such a big stink of it. It's a perfect example of something that just seems like a bunch of philosophy when you first hear it. It doesn't seem like science, and it definitely doesn't seem like math, and it doesn't seem like it has anything to do with any of the problems that we're trying to solve for an exam like this. I know it doesn't seem that way, but then I just want to remind you all that but people tend to say, and I had someone in office hours say yesterday, just exactly saying this, people will say, I can do the physics once it gets rolling, and I know how to do the equations and do the physics, but I just never know how to set up the equations, or I never know which equations to choose. I just never know how to start the problem. I don't know which equation to choose, but once I do, then I know what I'm doing. Right. Ironically, what people say semester after semester, what you're really kind of saying is, I'm okay with the mathematical computations, but I just don't know what physics to do to set up the mathematical computations. Like, in other words, everybody's always afraid of the math in this class, but it's actually the math that ends up being the easier part. The way to know how to set up, the way to know how to choose the equations, the way to know how to set up the equations, the way to know how to begin the problem, besides always do the 5-step method, is think in terms of Galileo's principle of relativity. Think when you start a problem, when you do step 1 DFP, when you do a diagram and fact problem, right there, you should make a choice of your coordinate system, what perspective you're watching the problem from, which specifically means make a choice and say, like, here's my 0. This direction is going to be positive from now on. This is going to be negative. And then here's the thing. And this, again, this is a compliment to Sarah. It's not a criticism. But like, once you say that down is negative, then every term that comes in that's down must be negative, and every term that's up must be positive. So yeah, that package started off by going up at 20. But the only way to really know that is to make sure that you're watching the problem from the perspective of the ground. If you watch from the perspective of the helicopter, it would seem like the package is going down. That's true. Anyway, okay. But I think she's totally cool. Now, one person in direct, someone's here. Sorry. Now, someone in direct chat is saying that they got 78.4 as their final distance. Wait, if that means as opposed to 80, if you mean 78.4 as opposed to 80, is that what you mean? Wait, let me just see. Hold on, let me think for 1 second. 1/2. Sorry, 2 times. Sorry. Yeah. If you're saying 5 times 16. Oh, yeah. If you're saying 78.4 as opposed to 80, that's totally fine. That's because you're using 9.8 for acceleration due to gravity, right? Yeah, which is totally fine. So that's a good, thank you, direct chat person. Great question. So this is to everybody. Can you use 9.8 on the exam? Sure, you can. But I'm also saying that you can use 10. Any time in this exam that free fall is involved and numbers are involved, you can always round 9.8 to 10, which secretly means I'm kind of saying you should, just because it makes your life much easier, and that's what all physicists do. There's no harm, but I will not mark off points either way. If you got 78.4 or 80, it's fine. It's just a lot of times these problems are designed, the numbers are designed to make things work out really nice and easy if you use 10. So it might just give you a strategic advantage. But yeah, 9.8 or 10 is fine. 78.4 or 80 is totally fine. Okay, so that was a good question, really. Are there any? I'll show you what I'm about to go over. I'll just show you on the screen. Hang on. Yeah, this problem right here is what I'm about to go over because it's the other big one of all the other big ones. They're solved in one class or the other. So, but if there's any other quick, okay, I'm looking at the chat. Oh, no problem. Oh yeah, no problem. Thank you, direct chat person. No problem. Thank you. Is there? Well, I guess I'm going to ask for a show. So this is the problem I'm about to go over, and it's very much like big old duck. Oh, chat, but wait, chat. Yeah. Wait. Right, exactly. So the free float problem, good question, direct chat person. The free float problem is the other big problem of this exam. And it might be the other hardest problem of this exam or the other, but that's totally what I spent so that's what I did in the other class and made a big video about. So, I could do it again, but I think it's more, but yes. So free float is what the other video, which will be posted and linked to your classroom, is about. So I'm thinking that I'm now going to go over the one remaining big problem, which is the one on the screen now. Can I just get a show of hands? Is it cool? Does it make sense if I go over this? Okay, cool. Okay. All right. Good enough for me. Okay. So that's what I'm going to do. Okay. And again, the notes for everything are all one packet of notes, one big PDF that will go, that includes both problems, and it'll go into your, okay. So let me put my board on and Jose, do you have a question or you just say, okay. All right. So all right, let's hope that the board works this time. Okay, that's a good sign. Okay, that's a good sign. Okay. Okay, so you see this. Okay, so this is all the solution to the riverbank, but I'm going to go on right here. Okay. Okay. Now this problem, okay, you can't, hopefully you can see it in front of you on your somewhere, but notice this problem does not give a diagram. You know, that's probably unfortunate, but that's all the more reason that you want to, in your step one, include a diagram. Like, do not think that you only put diagrams when there are diagrams, far from. So let me do a diagram. Always, have you noticed? Okay. Actually, okay. What else am I missing? Yeah, okay. 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 Sorry to, okay. So just, well, all right. So this is the situation. All right. And I don't believe I'm missing any information, but here's my diagram, right? And I'm drawing the diagram before I even know what the questions are. I'm just drawing the diagram. I'm labeling all the facts, all the pieces of information, even if I don't, you know, if I'm not going to even if I'm not going to use them all at once. Notice right away, this goes back to Sarah's question and to other things. Notice even before I'm asked in my diagram, what's the purpose of my diagram is, yes, labeling things, yes, putting down numerical facts and so forth. But really one of the huge purposes of my diagram is choosing a coordinate system and labeling it, i.e. I'm making clear, okay, this direction is east, that direction is west, that's up, that's down, east is called positive, west is called negative. It turns out it's going to ask me that anyway, but it doesn't matter whether it asks you. You want to do that right away. This is the Galileo idea, is like you choose your perspective and assign directions to your perspective. It's crucial because different answers will be gotten from different perspectives and different, anyway, you choose your perspective. So I've done that and I've labeled it. So I think these are all the facts of the problem. And I think that this is unknown. Yeah, okay. So question A, I mean, stop me if there's any questions or anything, but that's my diagram. So C diagram above. Okay, and then it says, what's the question? Assign coordinate systems. Okay, which I should do anyway and did. Assign coordinate system. So this is the question. Okay, so I've decided to call East, and there's no, okay, for this, there's no real, well, I could, if I really want to knock this exam out of the park, I could do a step 3 now, GDP, and write Galileo's principle of relativity. Because in fact, I'm going to do that. Like, why is it even asking me about coordinate systems, or why am I even thinking about them? Because the general principle here that I'm absolutely going to use and need is Galileo's principle of relativity. And this is what I would call form number 1. The laws of physics are the same in all unaccelerated reference frames or coordinate systems. The fact that the laws are the same in every unaccelerated coordinate system is what allows me to make a choice as to what coordinate system I'm using. In other words, the laws are the same, whether you call that positive or you call that negative. The laws are the same. The calculations and so the laws are the same, therefore I can do physics in one frame of reference or the other. But even though the laws are the same, and even though both coordinate systems will be equally legitimate, some coordinate systems are more convenient than others. And more to the point, the laws, let me back up. The laws are the same in all unaccelerated coordinate systems, but they hold independently in each coordinate system. So Galileo's principle allows me to make a choice, but it actually also obligates me to make a choice because I need to know what coordinate system I'm in once I start applying the laws. Otherwise, everything's going to get inconsistent and scrambled. So it's because of Galileo's principle that I'm even choosing a coordinate system in the first place. It makes all the difference in the world. But okay, anyway, so that's my GDP. Then step 3, I mean, I'm dragging this out a little bit, small. So step 4 for this particular application, I'm going to say East is positive. And I'm going to say that, and you notice in my diagram, I'm going to say down is positive because nothing goes up. Like, okay, you see, like often we make down negative, but in this problem, nothing's ever going to go up. So I want to reduce, I want as few negative signs as possible. So it's very convenient for me to make down positive. But something is going east and something is going west. So we're going to need it. So anyway, so that's also my answer. I'm circling it. Okay, so that I'm dragging this out. But so now by the way, you don't have to do that. You can make a different choice. But whatever choice you make, you have to stay consistent with throughout the whole thing. All right, anyway, so that's my A. So now B. Okay, for the time interval T equals, I'm looking at the time. Okay. See diagram above. That's my step 1. And what's the question? What happens to velocity and speed from T equals 0 to T equals 5? That's the question. Now, okay, so that's step 1 and step 2. Now, notice these questions are kind of straight for, I mean, they're like, what do you call it? Short answer questions, multiple choice type questions, and that's fine. That might make your life easier. But notice on an exam like this, I'm still, and I'm trying to watch the clock. But what I want to make clear to any of you who's listening is, even though we're giving choices for the answers here, you should still do the 5-step method and drag it out and explain as much as you can. I mean, it even does ask for a complete sentence of explanation. You can go beyond that. And show me that you understand where you got these answers from. So, I mean, so this is step 1. This is step 2. Wait, I'm hearing sounds. I think someone might be in the waiting room. Pardon me for a second. But step 3, GDP. What is it? Wait, what's going on in the waiting? Is some sound is happening. I hope I'm not leaving something out. The GDP, what it's really getting at here, if you notice, it's asking about what's happening with the velocity and with the speed. It's getting at the definition of velocity. It's getting at the fact that the definition of velocity, is displacement over time, or in other words, velocity is a vector quantity. Speed, well, velocity is a vector quantity. It has magnitude and direction. Speed is the magnitude of the velocity vector. Right? I'm just writing this down. This is the meaning of speed and velocity. Oh, sorry, no problem. No problem, direct type person. And you're doing great. I understand. Right. So I'm just writing this is my step 3 GDP. I'm saying it even before I answer the question. Like, here's the distinction, here's the relationship between velocity and speed. Now that I've written it down, I'll do step 4. I'll apply to the exact problem. So, someone's here. So from 0 to 5 seconds. So, all right. So now, so what's happening? From 0 to 5 seconds. To cut straight to the chase. Well, so oh, did my board just go? Wait, oh, what just happened? Okay, sorry. Okay, right. Do you see what I don't know if you can see what I'm doing, but I'm saying I was told that the coyote started at 25 meters per second, moving to the east, and I've labeled things so that east is positive. So at the first moment, the coyote is going positive 25 meters per second. And its acceleration is pointing toward the west. I've made west negative. So its acceleration is -5 meters per second squared. That's where I got the negative sign from, because I was told it was pointing to the west. So he's losing 5 meters per second of velocity every second. It literally, that's what the acceleration means. Like, in fact, I should say, this is also a GDP in a way. Average acceleration means change in velocity per time. And that's a vector quantity as well. So every second he's losing 5 meters per second of velocity, or his velocity is he's 5 meters per second of velocity is being subtracted from his velocity every second. So his velocity, so for these first 5 seconds, velocity is decreasing according to that chart. And what is speed? Speed is the magnitude of velocity. Speed is the magnitude of the velocity vector. So yes, the absolute value of each of those numbers is also going down. His velocities are going down, and indeed, he is slowing down. Right, so that is the answer. And all of that may seem like a bit of overkill. Like it might seem like overkill, like, duh, okay, his velocity is going down, his speed is going down. What's the difference? But to make it really clear that we're actually saying something here, or to make it clear that we really understand the distinction between velocity and speed and the whole trend of this motion, we're now going to question C, the contrast, the time interval 5 to 10. Like, there's going to be a different answer here. Otherwise, both of these questions wouldn't be asked. So the next question, so C diagram above, same thing. Oh, what? How are speed and velocity trending? One second. One second, sir. Okay. So from 5 to 10, now notice if we continue that trend, I want to make it clear, constant acceleration means that the acceleration stays the same forever. Like, even though at 5 seconds, the velocity hits 0, that doesn't stop the pattern. The velocities keep subtracting. They go into negatives now, right? So in other words, now the velocity will be -5, then -10, then -10, then -15, -20, -25, right? In other words, if this is all the Roadrunner, not the Coyote, sorry, but if the Roadrunner keeps doing this for a full 10 seconds, he's going to go forward for a while and then turn around and come back. This is exactly like what would happen. This is exactly like the package, honestly, in Sarah Marx's question about the chopper. Like, the package was going with positive velocity but negative acceleration. So it slowed down until it got to 0. And then it eventually had negative velocities that were getting increasingly negative. Acceleration, the sign of your acceleration means what direction you would eventually be velocitizing in. Or put another way, if your acceleration and your initial velocity are in conflict, you're eventually going to turn around. right? That's what happened to the package in the chopper. It had positive velocity, negative acceleration. Same exact thing here. This is a horizontal analogy to something being thrown up in gravity. In other words, I'm saying for these next 5 seconds, now I don't know, maybe I don't know if the coyote is going to hit the Roadrunner or not, but if it continued doing this for 10 seconds, what we would find is that the velocity continues to decrease, but the speed, please note, the speed is increasing now, right? I mean, that's why this whole thing is like worth asking. For this next, now, in other words, now this thing is coming backwards. This thing, the Roadrunner, would now be coming backwards, going faster and faster backwards. All the while, its velocity has been decreasing. It has constant acceleration. It's always losing velocity. The velocity numbers are getting smaller and smaller on the number line, no matter what. First, they're getting decreasingly positive, then they're getting increasingly negative. But that means that this thing was first slowing down and then speeding up. Please, make sure you understand, it's just an English question, but it's trying to get at the relationship between acceleration and velocity. And again, this is what the Roadrunner would do if he literally did have a constant forever acceleration that was in conflict with its initial velocity sign. Like, this is literally just like throwing something up in gravity. It literally is like the package from the chopper, which again is why it was such a perfect question that was asked for. Okay, now I've said a lot. We've got 23 minutes. That's the setup. Now there's 2 more questions. Will be easy. I mean, E is a straightforward question. D is where the work comes in. We've got 23 minutes to do the work for D, the central question. Again, the work I'm going to do now is just like the work we did for Big Old Duck. And also, it's just like the work in a way that we do for Lab 4. We're going to recognize that a 2-dimensional problem really is 2 one-dimensional problems occurring independently yet simultaneously. So D, how high was the cliff? Oh yeah, so assuming that the weight lands exactly on the Roadrunner, given all these facts. Now, and please understand too, I'm about to solve it. It's assuming all the facts given in the problem. The problem never says that the Roadrunner, the problem never says that the Roadrunner does run for exactly 10 seconds. It's just asking what would happen in 5 seconds or 10 seconds of its motion. But the facts given in the problem are the facts that are in my diagram. Sorry, right? So okay, so sorry, I'm getting myself. Okay. So my GDP, first of all, GPR form number 5, a 2D problem is 2 1D problems occurring independently and simultaneously. So that means this is just like Big Old Duck, the amount of time it takes the Roadrunner to get to a particular spot must be the same amount of time as it takes the weight to fall to that spot, right? They're going to meet at the same time. They're going to be in the same place at the same time. So, so this is like the big old duck setup, but it's different numbers and different details. With the big old duck setup, what I did was I looked in the y-axis first to find the time, and then I used that time in the x-axis. And that's also what you did in lab 4. But here, I'm not going to look in the y-axis first because I don't know how high the cliff is, right? In fact, that's what I'm trying to find out. What I'm going to do is look in the x-axis and figure out how much I have enough facts to know how much time it's going to take the roadrunner to get to that to the position of the cliff, right? So I'm going to look at the x. I'm going to use the x-axis to solve for time elapsed, time for roadrunner to reach the position of cliff. So I'm going to independently, okay, or I don't know if you had time to say. So I'm going to use the x-axis to solve for the time for the roadrunner to reach the position of the cliff. Okay, so I'm using the x-axis. In the x-axis, this is now all, I'm now looking at the particular problem. Step 4, PAW. Okay, in the x-axis, what I know is that x equals so I'm applying this equation, this one-dimensional constant acceleration equation to the x-axis. Okay, and I'm solving for time. So I know that x okay. Okay, no, right. So I just plugged in the maybe you in your exam, you maybe even should say like a equals -5, v naught, x equals 25, whatever, but that would be a good idea. But notice the numbers I just plugged into the equation, I'm carefully using their signs appropriately. Like the acceleration is to the west, so it got a negative sign. The displacement is to the east, and the initial velocity is to the east, so they got positive signs, right? Okay, so now and I'm solving for time. So I'm going to have a quadratic here. So I'm just going to try to make this a little bit. I'm going to divide both sides by negative. Well, here. Yeah. So do you see what I just did? You might want to write this in your notes or in the exam. I just divided both sides by -2.5, right? So that changed all the negative signs. I divided both sides by -2.5, right, to make it easier to deal with. Now I have a quadratic. You could use the quadratic formula here. Remember, I'm solving for t. T is a variable. This is just like big old duck. I could use a quadratic formula, but I'm hoping this is factorable. I think it is. I think we set it up that way. Yeah, I think like, right? So This is not an answer yet, but what this says, this is just like big old look. It says there's two possible times at which the roadrunner would arrive at the key location underneath the cliff. The roadrunner would arrive in 2 seconds at the rate he's going. But since we just established a minute ago that if the roadrunner is just left to its own devices and just went on forever, within 5 seconds, it would turn around and start coming back. So think about it. Like we're saying it would arrive. So that would be way out here past east of the cliff. The roadrunner is left to its own devices. It's running toward the cliff, running to the cliff. 2 seconds, it'll get to right directly below the cliff, but it's slowing down the whole way, slowing down the whole way. 3 seconds later, it would stop, turn around, come back, and then be at the cliff again, a total of 6 seconds later. If you think about the whole thing as being, if you think about 5 seconds being the moment when it will turn around, it makes sense. Like, in other words, note 2 and 8 are symmetric around 5, if you see what I mean. They're equal just around t equals 5. And t equals 5 is when it would turn around. So 2 is on its way out and 8 is on the way back. Hopefully that makes some sense to you. So now we use that time to go to the y-axis. The whole idea is that the x-axis and the y-axis are, the physics is happening in the x-axis coordinate system, and physics, the laws of physics are churning in the y-axis independently, like they're not affecting each other. It's just like the laws are happening in each coordinate system, but they're happening at the same time. So now, and again, this, and by the way, for those of you who are still with me, like this is a lot of physics work that I just did there, right? But if you're really following me, if you know in your heart, you're understanding what I'm saying, or if you know in your heart, you kind of get it, you're getting some of it, but some of it's still fuzzy to you. So you're making a note of what you want to think about later or argue out with your colleague later, which would be great. But anything that you're thinking about what I'm saying or understanding, or anything that I'm yelling at the top of my lungs about what I'm saying, that's what you want to explain in your work. Like, this is some good physics here on this page, but please let me tell you, you don't just want to hand this into me. Like, this is me helping you, but don't just hand me a sheet of equation, especially not if it's verbatim taken from mine equations. What you want to do is every time I'm stopping and yelling, that's an opportunity for you to write something in your notes or in your mind. And when you turn in your final draft of the exam, you would want to annotate this and explain what's happening. Like I'm about to say, like now the y-axis is happening at the same time. You put that in your words. Okay, so every time you understand something about why an equation was used or where it came from, like express that to me. The y-axis is occurring at the same time. You don't want your physics to look identical to mine. And the more you actually understand it, the more it won't. And since I have still 12 minutes, I'm watching the clock. Let me also, again, I don't want to just like over make a big deal of one person or something. Like on any given day, it's a different person. But part of what was great about Sarah's question is the truth of the matter is with physics, what it really means to understand physics and the kind of understanding that you want to express to me in your exam usually means having gone through a period where you did not understand something, and then you worked it out, and then you understand something. Like the thing that you'd want to express to me in the exam is any moment, anything that you can remember at one point being unclear to you, but is now clear. That means there's something conceptual going on. That's the thing you want to describe to me in the exam. Like literally, like Sarah would on the chopper problem, she literally could write down, like, at first it didn't make sense why the package didn't go anywhere at all. But then I realized like it was going up before it was going down, or blah, 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 blah. Everything is kind of a narrative of going from not understanding to understanding. So anytime you don't get something, like remember that. And then when you straighten it out, that's the story you want to tell. But anyway, all right. So now the y-axis is occurring at the same time. So, so use that time to solve for cliff height. In other words, so we're going to the y-axis now. Y again equals 1/2, or right? I'm just using the same equation, but I'm putting y subscripts in to make it clear that I'm now applying it independently to the y-axis. And now it's going to be a little, I'm not going to solve a quadratic again. Now I'm using time to solve for y. So here time equals 2 or 8. I'm going to solve for both answers. And v naught y equals v naught y equals 0 because the weight is just dropped. It could have been thrown or thrust or something, but it wasn't. It was just dropped. So the initial velocity in the y direction of the weight is 0, and ay equals g equals here will equal equals approximately 10 meters per second squared, and it's positive because down we said was positive, right? Because this is free fall. This is all, I'm still in step 4 PAW. Okay, so I'm going to solve for each time. Use okay, so y equals 1/2 10 2 squared plus 0 plus 0. And again, notice I'm using a positive number for 10 because I'm calling down positive. You could say, but wait, I don't like that. I like to call down negative. I thought gravity was a negative number. A lot of people say that a lot. You can make down negative if you want. You can make gravity a negative number, but then notice your displacement has to be negative as well because the package fell, I mean, the whatever fell down. So if you make the 10 negative, you've got to make, then your y is going to be negative as well. Just be aware of that. And that might, I mean, that's fine if you do all that. But okay, so y equals 5 times 4 equals 20. So, or y equals 1/2 10 times 6 squared, right? I think those were 2 different answers. Yeah. Were they 2 and 6? Yeah, 2 and 6, right? Okay. So equals 5 times 36, which is 180 meters, right? Yeah. So
Wait, Professor?
oh, sorry. Yeah. Yes. I'm sorry. Yes.
I think it was 8.
Oh, sorry. Was it? Oh, thank you. Great. 2 or 8. Oh, you're right. You're right. Thank you. Thank you. Thank you for paying attention too. And I can't even see. Sorry, who was that? Not that I should, but
It was Gianna.
oh, thank you, Gianna. Okay, awesome, awesome.
You're
Thank you.
welcome.
Okay, I'll remember you for the rest of my life as the person who corrected me. No, okay, no, awesome. Thank you. Okay. And so that's, but that you're totally paying attention. Thank you. Okay. Okay. So these are my 2 possible answers. So, oh, and there's things in the chat. Sorry, I was scribbling in there. I'll look in the chat in 1 second. I'm so sorry. Oh, maybe, I hope that doesn't mean I made another mistake. Well, I'll find out 1 second. But this is what I think. What this means is I think, well, let me just, before I make a big deal, look in the chat. Oh, it was it. Oh, sorry, wait. Sorry. Oh, yeah. Oh, I'm sorry. Okay, so this is kind of crucial what I missed in the chat. Okay. So I think this is the answer though, right? Someone's putting some very good questions in the chat. When we have 5 minutes left, so this is kind of perfect. They're good questions. I want to answer them, but I don't think there's any more mistakes. I think this is right. In fact, I think the best way I can really summarize this, hold on. Okay, I think I can address the things in the chat and summarize this whole thing. Let me just answer E. So the whole problem is totally finished so that you have everything from the whole problem. And I think E might even help make us understand D and so forth. Like I'm saying in D, there's two possible answers. The cliff was either at 20 meters, or the cliff was at 320 meters. Like, I don't know. It's one of those two places, because I think that this Roadrunner, given all the facts we were told, I think the Roadrunner is going to run out and then run back in. I don't know whether, I'm not saying the Roadrunner's planning that, but the Roadrunner's on a big rubber band in effect. Why do I know that? Just because the acceleration was given as constant -5, constant meaning forever -5, meaning the acceleration never changed. So that even when the Roadrunner hit a velocity of 0, it kept losing velocity, meaning coming back into the negatives. I'm not saying Roadrunners always do that. I'm just saying that's what the Roadrunner in this problem is doing. And if you think that's unrealistic, the really realistic version of this is if you had thrown the Roadrunner up, that's what would happen. It would eventually come back down, right? Now look, in E, but I still want to address the direct chat person. There's 3 minutes. In E, it says, suppose the Roadrunner obeyed a rule that when he ever stopped moving, he would never move again. Okay. If that were true, which is what sometimes people are picturing in their mind, that just because something stops, then it stops forever. So if the Roadrunner were to never start again once it stopped, then what I would say is, given all these numbers, the Roadrunner would have gone out for 5 seconds, and then stopped. How do I know 5? Because he started with 25 meters per second of velocity and was losing 5 every second. Like, that was my original calculation. Like, the velocities went 25, 20, 15, 10, 5, 0. So if we let 5 seconds go, the Roadrunner would go for 5 seconds and then stop, and that would be the end. And then I would say, okay, then the only time that the Roadrunner is ever going to be under the cliff is at 2 seconds, at the 2 second mark. So I would have only used that one time, the 2 second time, and I would have gotten the answer 20 meters is the height of the cliff. And that'd be it. That'd be the answer to this question. Like, if the Roadrunner just went out and that's it, then the Roadrunner would have hit the place of the cliff at 2 seconds, and therefore the weight only had 2 seconds to fall. So for it to fall for only 2 seconds, the cliff would have had to be at a height of 20 meters. But this problem didn't say that. The problem said that the Roadrunner continued its constant acceleration of -5 forever, which means that once the Roadrunner stopped at 5 seconds, it started coming back. Now, here comes the answer to the direct chat person's question. Like, if we allow the Roadrunner to come back for the last 5 seconds, everything should be symmetric. Like, whatever the Roadrunner is doing on the way out is a mirror image of whatever it's doing on the way back. Like, the velocities go 25, 20, 15, 10, 5, 0, and then -5, after 0, they go -5, -10, -15, -20, -25. So the whole thing would take 10 seconds then. 5 seconds to go out, 5 seconds to come out. 5 seconds to go out, 5 seconds to come back. So if the Roadrunner would be under the cliff at 2 seconds from 0, what I'm trying to argue, and I'm saying this to the direct chat person, 2 seconds from 0 is like the same place as 2 seconds from the end. Like, the end, when it gets all the way back to the end of this whole round trip, would be 10 seconds. What's 10 minus 2? It's 8. Like, 5 is over here, and 2 seconds, t equals 2 is 3 seconds before 5, and t equals 8 is 3 seconds after 5. Just like t equals 2 is 2 seconds from the beginning, and t equals 8 is 2 seconds from the end, if the end is 10, right? So I'm saying like 2 and 8 are symmetric around 5. Like they're the same place. It's just they're in the mirror images of each other. 2 is on the way out, 8 is on the way back. And so if the Roadrunner gets hit at 2, then that means the weight only had 2 seconds to fall. And as you see, it's 4:20. I'm going to stop in a second. Like anybody who has to go, you can go, but I'm going to catch my breath for a second and stay here to make sure, especially the direct chat person, please stay for a second so I can make sure you're cool with what but anybody else, you could stay for a minute, but you don't have to. But basically I'm saying if we only give the weight 2 seconds to fall because the Roadrunner gets hit on the way out, then the answer is the cliff must be 20 meters high. But if we give the weight 8 seconds to fall, then the cliff must be a lot higher. And the numbers say, the math says that it would be 320 meters high. So I'm saying this is all like big old duck, only it's like it, but the details are different. But to the direct chat person, that's when I said 2 and 8 are symmetric around 5. That's really what I mean. I mean, 2 is 3 less than 5 and 8 is 3 more than 5. And 5, what's magic about 5? 5 is the turnaround point. 5 is past the cliff where the Roadrunner would run out of steam and start coming back. So that's what I'm saying. Wait, I'm looking at. Wait, okay, so that's it. I mean, so you guys can go and I wish you luck tomorrow, but can I just ask at least that direct chat person to hang for a sec, or just ask him or her, did I answer I'm going to stop the recording too.